Hey ChemStars, it's Ms. Macaulay. We're going to go over the first objective check for chapters 10 and 11 gas laws, and this is the objective check on kinetic molecular theory and Dalton's law of partial pressures. So the objectives we're covering with this is that you can understand and state the basic tenets, that means the basic ideas of KMT as they relate to gases, and that you can also use Dalton's law of partial pressures to solve for the total or unknowns in the system. Okay. So number one, we didn't do this activity in class, but Mrs. Van de Walle modeled it in the notes and using the PhET simulation. So if you imagine that you're a moving molecule of gas, the pressure is related to what? The speed at which you walked? No, that's not right. The speed was related to the energy and to the temperature. The amount of space? No, that's related to the volume. It's the number of collisions. It's those actual collisions between the particles and against the walls of the container. That is what your pressure is. Question 2. As the volume of a gas decreases and everything else is held constant, the pressure increases. It goes up. There's more collisions, particles are closer together and bumping into each other in the walls of the container more often. So if volume goes down and pressure goes up, like we saw in number 2, pressure and volume are indirectly related. So one down, one up, and vice versa. Now we come to the Daltons Law Problem. Hydrogen gas is collected over water at 35 degrees Celsius. The first thing you should be thinking about is that when I have the gas, it won't be pure hydrogen. There'll be some water vapor that comes off the surface of the water as well. Make sure you go back to the notes and to the slides, see some pictures of what this would look like. If the total pressure of the gases above the water is 1.02 atmospheres, what is the pressure of the dry hydrogen gas alone? And they give you your conversion factor here. 1 atmosphere is 760 millimeters of mercury. So why do we have to do that? Because the table you're given is all in millimeters of mercury. So the first thing is we've got to convert our 1.02 atmospheres for the total system into millimeters of mercury. So how do we do that? We take our 1.02 atmospheres over 1. This is our factor labeling. You could say question mark atmospheres. Oh, I did that backwards. You could say question mark millimeters mercury is equal to 1.202 atmospheres over 1. We want to cancel atmospheres and go to millimeters of mercury. And so your final answer is going to be 7.752 millimeters of mercury. So if you want to double check in your calculator, we're taking 1.02 times 760, and you get 775.2. Now, is that the right number of sig figs? Oh, Pickles is barking again. Okay, so we're not going to worry about sig figs yet because we still have to use this number to answer another problem. We'll come back at the end and look at that. So what is the pressure of hydrogen in millimeters of mercury? So we know that the total pressure of the system is the combined pressures of each of the constituent gases. So the hydrogen and the water vapor are 2 parts. So the total pressure is that 775.2 millimeters of mercury. And we are solving for partial pressure of hydrogen. And what's our partial pressure of water vapor? Well, in the Pickles is very upset about this. So the water temperature was 35 degrees Celsius. So we use the water vapor pressure versus temperature. We look at 35 degrees. And at that temperature, the partial pressure of water is 42.23. So we know that the total system is equal to hydrogen plus that 42.23. So how do we find what's missing? Well, we just subtract that over. So 775.2 minus 42.23. And we get 732.97. Now, technically, on this part of the problem, we were adding and subtracting. So you go to your least number of decimal places. Here I kept that tenth, but here it goes to the hundredths. That means technically to my answer here, I should only really be precise to the tenths. Well, that's going to bump it up. So we'll actually go 733. Well, that doesn't actually have the tenths now. So we'll add a 0.0, and that's our millimeters of mercury. Okay. You could have chosen to do Form A or Form B, so I'll go over both answer keys now. So here's Form B, very similar, just some different numbers. Temperature is related to the speed at which you walked. So I know we didn't do the outside activity, but imagine you're the moving molecule. When you're moving around, your energy is the speed at which you walk, which is the same as your temperature. As the volume of a gas decreases, the temperature also decreases, all other things being held the same. So temperature and volume are directly related. Now here's the Dalton's Law problem for this one. Now this time, we're collecting hydrogen gas over some much warmer water at 55 degrees C. So we look at our table to find our partial pressure of the water vapor in millimeters of mercury, but the problem gave it to me in atmospheres. So same thing, I'm looking for question mark millimeters of mercury, and that's equal to the given. Put it over 1 so you can see your nice fractions canceling out. We're canceling atmospheres and going to millimeters of mercury. Take out your calculator, and we're going to take 0.988 times 760. If you want to, you can divide by 1 so you feel better, but it's the same thing. We get 750.88, and that unit is millimeters of mercury. I'm not going to round this for sig figs because I need that number to be used later. If you did want to use it, since I'm actually multiplying, we would have to go to 3 sig figs to 751, but we don't want to do that yet because we'll lose some of the precision for the adding and subtracting. So just like the previous form, total pressure is the same, or is the sum of hydrogen plus water's partial pressures. So we know total pressure is 750.88. We don't know hydrogen, that's what we're trying to solve for. And the water pressure, we read off of a chart. You'll always have this chart available to you. So how do we get water away from this side? We have to just subtract. So we take our total pressure minus the 118.2, which is the partial pressure of the water vapor, and we get that the partial pressure of hydrogen is 632.68. And remember, when we're adding or subtracting, technically we're conserving the least number of decimal places, so we're going to go to the tenths. So here's my partial pressure of hydrogen. So that is Dalton's Law and the basic kinetic molecular theory. Good work today, guys. Remember, don't wait to be great.